this lesson, you'll learn how to add and subtract complex numbers and multiply and divide complex numbers. How do complex numbers apply to polynomial equations? Consider the equation 2x squared plus 2 equals 0. If you solve this equation for x squared, the result is x squared equals negative 1. Since there is no real number whose square is negative 1, the equation has no real solutions. French mathematician René Descartes proposed that a number I be defined such that I squared equals negative 1. Since I is defined to have the property that I squared equals negative 1, the number I is the principal square root of negative 1. That is, I equals the square root of negative 1. I is called the imaginary unit. Numbers in the form 3i, negative 5i, I squared of 2 are called pure imaginary numbers. Pure imaginary numbers are the square roots of negative real numbers. For any positive real number b, the square root of negative b squared equals the square root of b squared times the square root of negative 1, or bi. We can use that to simplify the square root of 28. We can rewrite it as the product of square root of negative 1 times the square root of 4 times the square root of 7. I know what the square root of 4 is. It's 2. And I am used to putting my I at the very end so the whole number part is together. But this book prefers not to do that because some people are sloppy and let their radical sign go over the I, and it doesn't make sense to have the square root of negative 1. So this book chooses to put the order such as 2i square root of 7. So they always put the radicals at the end, so for sloppiness you can't end up with a radical over an I. We can use the same principle here, and we'll write it as the square root of negative 1 times the square root of 16, square root of 2, square root of y squared, square root of y. So I know the square root of 16 is 4, the square root of y squared is y, and then they're going to put the I next for order for the square root of negative 1, and then what we have left in the radical is 2y. Now, since we took the square root of y squared, we went from an even exponent to an odd, we should put absolute values around the y to make sure it stays positive. The commutative and associative properties of multiplication hold true for pure imaginary numbers. So I can use those properties to rewrite negative 3i times 2i as negative 3 times negative 2 is negative 6, I times I is I squared. But we know that I squared equals negative 1, so it would be negative 6 times negative 1, which equals 6. We've got square root of 12 I can rewrite as square root of 3 times square root of 4 times square root of negative 1. And square root of 2 I can write as square root of 2 times square root of negative 1. I know what the square root of 4 is. It's 2. Square root of 3 times square root of 2 is square root of 6, and square root of negative 1 is I. So if we have I times I, that's I squared. Oh yes, and square root and square are inverse operations. So I guess instead of I squared there, I could have just put negative 1. So my final answer is going to be negative 2 square root of 6. Now, I squared is our magic number to simplify with. So I can rewrite any multiple of squared as I could go 2 times 17 is I to the 34, and I need another I to make 35. So again, 2 times 17 is 34, and then power times power we add exponents, so plus one more would be 35. So these are equivalent expressions. And we know I squared is equivalent to negative 1. And negative 1 raised to an odd power is still negative 1. So my final answer is negative I. Now, of course, if we had negative 1 raised to an even power, it'd be positive 1. We like simple directions, just says solve. So the first thing we need to do is subtract 20 from both sides. So I have 5y squared equals negative 20. And then I need to divide both sides by 5. So y squared equals negative 4. Now up until this lesson I would say I can't take the square root of a negative, I get no real solutions, which is true, because what I'm going to end up getting is square root of 4 times square root of negative 1, and when we take the square root, it could be positive or negative. Square root of 4 is 2, and square root of negative 1 is I. Consider an expression such as 5 plus 2i. Since 5 is a real number and 2i is a pure imaginary number, the terms are not like terms and cannot be combined. This type of expression is called a complex number. A complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is the imaginary unit. A is called the real part and b is called the imaginary part. The Venn diagram at the right shows the complex number system. If b equals 0, the complex number is a real number. If b does not equal 0, the complex number is imaginary. If a equals 0, the complex number is a pure imaginary number. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. That is, a plus bi equals c plus di if and only if a equals c and b equals d. Find the values of x and y that make the equation 2x plus yi equals negative 14 plus 3i true. Well, using the definition we just had, that means 2x must equal negative 14 and yi must equal negative 3i. So we have two very simple equations to solve. So I can divide both sides by 2, and I have x is negative 7. Oh, and I guess I already know that y had to equal negative 3. To add or subtract complex numbers, all we need to do is combine the like terms. So I'm going to add the 3 plus 2. I'm using the associative property of addition. And the 5i and the negative 4i. So I get 5 plus 5 minus 4 is just 1i. We don't normally write the coefficient of 1. The form a plus bi is called the standard form of the complex number, so it's preferable to write the real part and then the complex. Again, I can regroup and have my real part, so 4 minus 3, and my imaginary part, so negative 6, and then it was minus negative 7i, so plus 7 for the I parts. So 4 minus 3 is 1, and negative 6 plus 7 is also 1, but once again we don't normally write 1 in front of the variable. I is not a variable, but it sure looks like one. Electrical engineers use J as the imaginary unit to avoid confusion with the I that they use for current. Why not just use C for current? In an AC circuit, the voltage E, current I, and impedance Z are related by the formula E equals I times Z. Find the voltage in a circuit with current 1 plus 4J amps and impedance 3 minus 6J ohms. I plugged in 1 plus 4J for the current and 3 minus 6J for the impedance, and then we can FOIL. So 1 times 3 is 3 minus 6J plus 12J minus 24J squared, but we know that J squared or I squared is negative 1. So we have 3 plus 6J plus 24, and combining my likes, 3 plus 24 is 27 plus 6J. And I remembered to write the real part first and then the imaginary. Two complex numbers of the form a plus bi and a minus bi are called complex conjugates. The product of complex conjugates is always a real number. For example, if we multiply 2 plus 3i times 2 minus 3i, 2 times 2 is 4, minus 6i plus 6i, minus 9i squared would be the same as plus 9. The i's are going to cancel out, so all we have left is 4 plus 9 is 13. You can use this fact to simplify the quotient of two complex numbers. So just like we got radicals out of the denominator, we're going to multiply by the conjugate of the denominator is 3 minus 2i over 3 minus 2i, and this works because anything divided by itself is 1, and when you multiply a number by 1, even if it's a weird looking number, it's still equal to what it was. So we can distribute, and we're going to have 15i minus 10i squared, which would be the same as plus 10, over 9 minus 6i plus 6i, and then positive 2 times negative 2 is negative 4, but then I times I is I squared, so we'll change that to plus 4. And of course, our opposites cancel out. So we've got 15i plus 10. And in the denominator, 9 plus 4 is 13. Standard form, we're supposed to have the real part first, so I have 10/13 plus the imaginary would be 15/13 I. Okay, this is a step easier than the last one. We just need to multiply by I over I, because I squared is negative 1, that's all we need to get rid of. So when we distribute, we're going to have 4i minus I squared, so plus 1 over 5i squared would be negative 5. My real component was negative 1/5, positive 1 divided by negative 5, minus 4/5 I. I squared equals negative 1, and I equals the square root of negative 1. Complex conjugates can be used to simplify quotients of complex numbers.